Right, in this video we're going to describe what is called a recursive sequence. A sequence is just a pattern of numbers, and a recursive sequence essentially is a pattern of numbers that just builds from one number to the next. So you'll notice the two recursive sequences given here. There's one at the top of the screen and one at the bottom. And in both sequences, that first term is given. So you'll notice that a sub 0, essentially saying the zero term, the initial term, is equal to 3 in the top one. And on the bottom it says a sub 0 equals 2. So the initial term is given as 2. The reason we need that is the formula, the actual recursive sequence formula, is given right below it there. So where you see that it says a sub n equals a sub n minus 1 plus 5. What that means is if I go to try to find a sub 1, so if I take my pen and we go find a sub 1 equal to, and I apologize for the clicking, my pen makes a little bit of noise, but a sub 1 equals, well, if n here is 1, then in my next term, that means that's a sub 1 minus 1. And then, of course, the large plus 5. Well, if that sub number is a sub 1 minus 1, then a sub 1 is really equal to a sub 0 plus 5. And what I can do is take out a sub 0, that we know up here is equal to 3, and a sub 1 is really equal to 3 plus 5 equal to 8. So 3 plus 5 as in the previous term, a sub 0 being the term before a sub 1. We're going to use the term before, or essentially if I'm looking for a sub n, I'm going to use a sub n minus 1, the term one step before n. And I will find my term that way. So then if I want to go on to find a sub 2, it'll be the same idea. 2 minus 1 would have been a sub 1 plus 5, or basically my 8 plus 5, which is equal to 13. A sub 3 is the same idea. 3 minus 1 would have been 2. Since a sub 2 was 13, I'm going to add 5 to that. So I get 18, and so forth and so on. So if we're finding the first 5 terms of the sequence, as it says up here, basically a sub 4 will be the term before that, a sub 3, because 4 minus 1 would have been a sub 3. So 18 plus 5. And then a sub 5 is the same idea. I'm going to take a sub 4, or 23, plus 5, which is 28. Essentially, again, you're using the term just previous to a term. So notice in the blue box up here it says a sub n minus 1 is equal to the term previous to a sub n. Now, you can also write it as we did in the sequence down below. It's also a recursive sequence. Notice there, again, a sub 0 equals 2, but a sub n plus 1, so essentially the term one term after n, is equal to a sub n squared. So if a sub n is the term we're on, a sub n plus 1 would be the next term. If we want to find a sub 4, now the downside to that is, if we were using what's called an explicit sequence, I could plug 4 in and just go get term number 4. But in a recursive sequence, in order to find term 4, I need to know term 3. In order to find term 3, I needed to know term 2. In order to get term 2 and term 1, I needed to know term 0 in order to get term 1. And luckily, I do know term 0. So to get term a sub 1, well, if 1 is supposed to be n plus 1, then n must have been 0. So I'm going to take term 0, or basically a sub 0 squared, because again, if 0 is in here for n, then 0 plus 1, I'm finding a sub 1. So that's 2 squared, which is 4. A sub 2 will again be the term previous to that. If a sub 0 got us a sub 1, then a sub 1, or 4, should get us a sub 2. And that one becomes 16. a sub 3 will be 16 squared, or the previous term squared, which I believe is 256. And then a sub 4, I'm probably going to need to get my calculator out for that one, because 256 squared is going to be a fairly large number, and that is not one that I have memorized by any means. So that comes out to 65,536. And that should be a sub 4. So again, the idea is you're using a previous term, a sub n, to go get term a sub n plus 1. A sub n plus 1 being the term after a sub n. And that's generally how recursive sequences work. They flow from one term into the next, into the next. You're using the previous term to go get the next one. Now, we do recursive sequences in our head more often than we think of. Basically, a recursive rule, if we wanted to write our own recursive rule, all we really need to figure out is, how do I get from one term to the next term then? So in this first sequence, you'll notice I'm going from 2 up to 14, and then from 14 to 98, from 98 to 686. The first thing I would double check is it a formula that we're already familiar with? So let's think simple operations. If I wanted to get from 2 to 14, right, I would just have to add 12. That'd be a simple arithmetic operation. But if I just add 12 again, I should have gotten 26, and that's definitely not 98. And again, 98 plus 12 would definitely been 110, not 686. So it does not seem as though I'm just adding the same number every time. If addition doesn't work, how about we think of a different operation? Obviously, we're not subtracting, we're not dividing, so we're not getting smaller numbers, but maybe we're multiplying. So if we think about it, to get from 2 to 14, we would multiply by 7. To get from 14 to 98, we'll just verify very quickly, 14 times 7, which actually is 98. If I multiply by 7 again, it's 686, and that seems to be our pattern. Again, you can just quickly use your calculator to verify those numbers. But if we just multiply by 7 over and over again, that seems to be working. Well, in that case, I just want to take my terms. So let's just say that a sub 0 is 2. Well, to get the next term, a sub n, we're going to use the previous term. So remember, if we're looking for term a sub n, the term before it would have been a sub n minus 1. And we really just want to take that right now times 7. Because remember, we're multiplying by 7 over and over and over again. One term times 7 gets you the next one. That term times 7 gets you the next one. So we'll just multiply that by 7. And again, you need both parts of that to define your sequence. But that's one way to come up with a recursive rule. So take a second. I'm going to let you think about it. But take a good look at what's already on the screen and see if you can't come up with a recursive rule for these two sequences. And then I'll come right back here in just a few seconds, and we'll put the answers on the screen for you, and you can kind of double check. Okay, so the sequence in the upper right, you'll notice, again, I would just check basic operations. How do you get from 19 to 13? And I noticed that we would just subtract 6. Well, 13 minus another 6 would have been 7. 7 minus another 6 would have been 1. And 1 minus another 6 is negative 5. So if we just want to subtract 6 over and over and over again, define your first term. So I would call that a sub 0, the initial term, is equal to 19. And then any term that we want, a sub n, is equal to a sub n minus 1, the term right before a sub n, minus 6. And again, make that a big minus 6. This n minus 1 needs to be a sub number. It's written very small and to the lower right, kind of like a base of a logarithm. It's a very small number written to the lower right. Again, it's not the actual number we're plugging in. It's just denoting which term we're on. So again, 19 is a sub 0. 13 would have been a sub 1. 7 is a sub 2. 1 is a sub 3. And so forth and so on. Now the sequence on the bottom is a little bit tricky, but hopefully after looking at it for a little while, you realize that 1 times 2 is equal to the next number, and 2 times 2 would have been 4, and 2 times 4 would have been 8, and 4 times 8 is 32. I know that's a tricky sequence, but again, there's a lot of patterns out there, and you got to look and kind of think outside the box sometimes. So in order to do this, though, we're going to have to use 2 terms to go get the third term, which means we're going to need to define, again, those 2 terms. I can't find this second term because I would need 2 terms before it, and I only have 1. So we're going to say that a sub 0 equals 1. We'll also define a sub 1 is equal to 2, this 2 right here. That way we can now say, well, hey, a sub n is the term previous to it, so a sub n minus 1, times the term previous to that. So we'll call that n minus 2. Or if n minus 1 is 1 step back, n minus 2 is 2 steps back. But if I multiply 1 step back times 2 steps back, so 2 and 1 made 2. Again, 2 and 2 made 4. And 4 and 2 made 8. That should get us our terms. Now, that one reminds me also, as long as we've now learned how to go forward and backward with recursive sequences, we kind of know everything we need to know about those. But there is a very famous recursive sequence that we may as well bring up while we're at it. It is called the Fibonacci sequence. And the idea of the Fibonacci sequence, very similar to the one we just did, only its addition is that it's going to use 2 terms. It's going to use the term 2 steps before, n minus 2, and the term 1 step before, n minus 1. So that's 2 steps back, again, and 1 step back. So in order to find it, we're going to need to know these terms. A sub 0 is 1, and a sub 1 will be 1. And basically, we're going to add the 2 terms together to get the next term. So a sub 1, or a sub 2, sorry, would be 2 minus 2 is a sub 0, plus 2 minus 1 up here would be a sub 1. Or basically 1 plus 1 is 2, and we've got it. So to get a sub 3, again, we're going to add the term 2 previous to it. So a sub 2, a sub 1, to the term 1 step before it, which would have been a sub 2 that we just found. So that one will come out to 3. To get a sub 4, again, I have to go 2 steps back and add that on to 1 step back. And same thing for a sub 5. Go 2 steps back and add that on to 1 step back. Oops, random line on that one. Let's see if we can get rid of that very quickly here. There we go. And finally get ourselves an 8. So we found our, essentially, first 5 terms, 2 of which were given, and then we found the next 3. Okay? We found the next 3. So we found a sub 2, 3, 4, and 5, actually the next 4. All right. Again, the Fibonacci sequence is just a fairly famous one. If you want to know more about it, I would look up the Fibonacci sequence online. There's a lot of great information, a lot of information about how it relates to the family tree of bees, if you will, drone bees, and how there would be 1 and then 1. And drone bees have kind of an interesting, genealogy, so feel free to look up their facts. Or there's also terms about the golden ratio. If we kind of divide the terms of the Fibonacci sequence, we zone in on this ratio called the golden ratio, and it has a lot to do with various different forms of art throughout history. So the Mona Lisa will be tied into it, a lot of Greek architecture is tied into it, nautilus shells, or it's found in nature a lot. Again, an incredible wealth of knowledge there, but feel free to look up the Fibonacci sequence online and learn much more about it. And again, you can also look up recursive sequences if you like. Again, how to take numbers and find their sequence, or just take the sequence and find their terms. But good luck with that, and if you have any questions, be sure to talk to your teacher. Otherwise, good luck, and have fun.